In this problem we need to find the value of R for which the current through this branch will be 4 amps. So we can see that here is a current source, the source is a current source, this one, and it's 20 amps. So we know that current in this branch is 20 amps, and this current will be split here. 4 amps will go in that direction and 16 amps will go in that direction. We don't know the value of R here. So we will start to develop a rule called current division rule using this problem, but to do that, what we will do, let's say the voltage drop here is V0 maybe. So we know that V0 will be, if this current is, let's label it as I1, though we know the value, but we will just try to write an expression, so that's how we will go. So I1 times, and let's say the whole resistance is R1, that will be equals to I2 times R. I'm just writing R, it could be R2 though, maybe for R2, so R2 is equal to R basically. So that's that. So we can write then I1 over I2 over I1 will be equals to R1 over R2, that we know, R1 over R2. Now I2 will be R1 over R2 times I1. Now we do not know the value of I1, let's say. Here we know, and we can actually solve this from that. So first we will do that, but if we do not know, what we will do? So let's first do this. We need to find actually R2. So R2 we can write R1 over I2 times I1, and R1 is of course the total resistance of this branch, which is 40 plus 80, so that's 120, divided by I2 is the current in that branch, which is 60, and this is in 4, so this is 4 and that's 30 ohms. So our problem is solved, which we wanted to, but I want to develop the current divider rule as well. So let's say we didn't know what is the current through this branch, but we knew the resistance. So what we can do, this is our, I will start from here again. So I2 is equal to R1 over R2, R1 over R2 times I1. Now what we can do here is, we can write these two resistances, which is R1 R2, these two are in parallel, so we can find what is the equivalent resistance, which will be R1 times R2, R1 parallel R2, which is R1 times R2 we know, divided by R1 plus R2, that's the parallel resistance. So if we want to replace these two branches by just one single branch, we could have written, let's say RP, then the current would be the main current. So basically the current that is here, these two branches are replaced by one branch, so this current, which is 20 amps, but if we didn't know, let's call it I. So I is equal to I1 plus I2. We are trying to develop the rule here, just the expressions. So this I would flow through that RP, because we have replaced these two as a single resistance. So then we can write V0 is equal to I times R1 times R2 divided by R1 plus R2. Now if we go back here, which is this one, so we can write V0 is equal to I1 times R1 equals to I2 times R2, or I times R1 times R2 divided by R1 plus R2. So we can write that, because these are all V0. This is V0. These two were parallel branches. So this is V0 when we consider just this branch, I1 times R1, or when we consider this branch, it will be I2 times R2. But when we replace these two parallel resistances by a single resistance, that will be RP, then we will have to, RP is this one, and that will be multiplied by the total current, because both the branches are replaced by single branches, single branch. So we can equate from this and this, we can equate these two. So I1 becomes R1 getting cancelled, so that's R2 divided by R1 plus R2 times I. Similarly, from these two we can write I2 equals to, what would happen in this case is R2 will get cancelled, so R1 here, R1 plus R2 times I. So these two are the current divider rules basically. So what it says is, if we have two parallel branches and we know the resistance of these two branches and we know the total current here, we know the total current, let's call just I, as we have written in our expressions. So total current is I. So current I1 and I2, that's these two we don't know, so we can write them from this expression. So I1 is, in the denominator we have sum of the two resistances, as we can see, sum of the two resistances multiplied by the total current in the numerator, of course, not denominator. And then in the numerator the other thing is, the other term is the other resistance. So if we are trying to find the current through resistance R1, the numerator will be multiplied by R2. So we can write this one actually like this. So this is I divided by R1 plus R2. This is common here in both expressions. So I divided by R1 plus R2. So we have two parallel branches here. When we are trying to find I1, this will be multiplied by R2, and when we are trying to find I2, this will be multiplied by R1. And that's how we can see that when the resistance is smaller, the current is higher. So if this is big and bigger and this is smaller, this current will be bigger and this will be smaller. So R2 is bigger, that means I1 will be bigger and I2 will be smaller. So this current is through that branch and this current is through that branch, so it makes sense, and it's probably not hard to remember because it applies for two parallel branches, but it's extremely useful when we do solve circuits. This rule comes handy most of the time.